Okay, so starting off with double integrals. Okay, so the double integral we can use to compute the volume of any like 3D object. So you always do the double integral of some function. So Fubini's theorem for rectangular regions. So this is the less stronger form of Fubini's theorem, but it says that if you're integrating over a rectangular region, so x is between two numbers, y is between two numbers, then you could do the double integral with respect to dx dy or dy dx. You can switch the order. And because these are all constants, when you change the order or rearrange, you don't have to think about, oh, what function is it going to change to instead? You could just simply switch the bounds and switch the dx dy. That's only for rectangular regions. So for example, let's do this example. So it says, compute the double integral of some function, which we're given, for the region is this rectangular region. And you know this is a rectangular region because your x is between 0 and 1, y is between 0 and 2. So you can imagine like a purple rectangular region down there. And this is the picture of our graph, of our function, by the way. So you have a purple rectangular region, and you're imagining like taking the volume like down here. So if you have a region, you have this U thing, and you're taking the volume of this shape. Then what do you do? Well, if we want to do the integral from dy dx, so this means that we start from y. So we draw a line. Well, they give us that y is between 0 and 2, so we can just write 0 and 2. And they give us that x is between 0 and 1. Okay. And the way double integrals work is they start inward and move outward. So the dy is the first integral and the first like d term. The dx is the next outer term, and then it would keep going on if you had triple integrals, four integrals, etc. And so for this question, you do like 0, 1. What's the integral of this with respect to y? So everything else is a constant and y is your variable. So you would have 10y plus x squared y plus 3y cubed over 3 from y equals 0 to 2. And notice that I'm writing like what variable I want to use so that we can keep track of where we are going to plug things in. Otherwise, things can get messy when you have more integrals. Dx. And so this would give you 20 plus 2x squared plus 8 dx. And you can integrate with respect to x, and then you'll get 86 over 3. Any questions on this example?
That's a good pick.
Yes. And all the notes are always posted on my website. Yep. Okay, so a nice feature about the rectangular regions is that, so let's work out an example. On the left side here, we have this double integral of x, y, dy, dx. We can compute this integral. So the integral with respect to y would be xy squared over 2. We plug in 0, 1 dx. We get this integral, x over 2 dx. We get x squared over 4 from x0 to 1, and we get a 4. But on the right side, what happens if we split up these integrals? So I just took everything with x's and I put it as our first integral. And then I took everything with the y's and I put it as our second integral here. You'll notice that, what is this first integral? So integral of x is x squared over 2. Integral of y is also y squared over 2. We get a half times a half, which is 1/4. So we see that we got the same exact answer both ways. And more generally, we saw that the double integral of xy, dx dy, equaled the integral of x dx times the integral y dy. This only worked because, first off, our bounds are numbers. So as I said, for rectangular regions, we can switch the bounds no matter what. So our bounds are numbers. And this expression here, we can write as some function with respect to x, so x is a variable, and a function for y is our variable. So in this expression, if we can split it up into something with some variable times a different variable, then we can divide those, separate those integrals. So more generally, this integral equals like this. And you'll see in one of the practice problems, you end up getting this like way longer version where x1, x2 are all like your different letters, different variables. Any questions on this idea? Okay, so then we have Fubini's theorem, which is the stronger form. So the thing we just did previously, that was just for rectangular regions. Now, what if your region is like some weird triangle or other general regions? Fubini's theorem basically just says that you do your double integral and you could either do dy dx or dx dy. Note that when you're doing this double integral, this first inner bound, so because we're doing dy first, these bounds can have x's in them. So you could have like from y equals x to x squared. But if you see something that looks like y equals y and then 2y or something, you know that that can't be, because these bounds should have things in terms of x or they are constants. And then your outer bound is always going to have to be constants. And so if you do dx dy, you'll see that these first bounds, they can't have x's in them. They have to be terms with y's in them or numbers, constants. Yes.
Why?
Because doing y equals y doesn't make sense, because how would you graph y equals y, right? So these terms have to have x's in them, so that say y equals x, you have some region where your y like line is entering at this line, and then it exits at like some other line here. So you can have terms in terms of x or constants. But yeah, that's the like definition. If I noticed in the study guide, he said like you might need to know. Let me go check. Like what an integral over a domain means. So in terms of summing up values over small bits and taking a limit. So if you want to read more about that, that is in the textbook. So chapter 15 in the textbook, if you want to read in the textbook, like on my website. Okay, and you could just find it online. Okay. So let's do an example. Yes.
Wait, so for the general region, you can basically reorder and then change the balance as you.
Yes. Yep. Okay. So let me explain one example. Okay, so we have this double integral and our function is sine x over x. The function is fine. What's important is the bounds. So for the bounds, what do we want to do? If we want to make our order like some integral with dy dx, this means that we first start with dy. So we draw a line in terms of increasing y, so meaning like upward, vertically upward. So I'm going to draw this orange dotted line. We see that it's in the direction of y, increasing y. So where does this line enter? It enters at this point. What is that line? That line is y equals 0. Where does it exit? Well, it follows the line. It exits at this line. So that line is y equals x. So enter, exit. So your y goes between 0 and x. And that's what you will use for your bounds. So y equals 0 to x. Then you look at all of these possible orange lines. So all of these upward vertical lines, out of all of these, what is the smallest x value you can get? The smallest x value you could get is here. So that is where x is 0. That's where it enters. What's the largest x value you could get out of all these lines? 1. So it exits at 1. So your bound is x from 0 to 1. So you do the double integral of your function, which is sine x over x, dy dx. Okay, and you can, so let me do the first step. When you do the integral with respect to y, notice that this term just has x's in it. So it's acting like a constant. So this integral is sine x over x, y. And you're plugging in y from 0 to x, dx. Then you get sine of x over x. So you plug in y, x equals for y, and then plugging in y equals 0 just gives you 0. So you're left with this, or the integral of sine x dx. And then when you simplify, you'll get negative cosine 1 plus 1. Yes.
With the lines that you drew pointing upwards, is that like the direction you slice, or is that just like how you see the difference? Like, is she doing dy first? So she's like you
Yes. So if you're not really like slicing anything. These dotted lines are just to help you see where you're entering. So what the bounds are. So entering is your like lower bound, where you're exiting is your upper bound. So you're like drawing these lines, and you see that you enter here and exit here.
Okay. And you drew them that way because of this dy.
Yes, dy.
Okay.
So then if, say, using the same example and we wanted to do dx first instead, then instead for dx, you want to draw lines in terms of increasing x. So in the increasing x direction. So because x, this axis is this way, so you would draw this purple dotted line this way for dx. And so where is it entering at? It enters at x equals y. Where does it exit? It exits at x equals 1. Then out of all the possible purple lines, the smallest y value is 0. The greatest y value is 1. So this is 1, this is 0. So if you wanted to do dx dy instead, your integral would be dx dy sine x. So you do x first, x equals y to 1. And then y from 0 to 1. Any questions about that? Okay, a couple rules. So properties of like double integrals, I'll just say these quickly. There's the constant multiple rule. Just like normal integration, if you have like a constant c, you can take it out. So that makes integration easier perhaps. Also sum and difference. If you have the double integral of f plus g, you could separate that. You have domination, where if your function is always greater than or equal to 0, then that double integral will also be greater than or equal to 0. And additivity, this is the nice one, is where if you have some big region, for example, I have this big region A, we're given A, and we're given this other region B, and you're asked to find the area of this region C, then you could say that A should equal B plus C. So that's what additivity is saying. If you have two regions, this purple one and the red one, which add up to the black one, then you could add those regions. Any questions on that? Okay, so in the last example, up here, we saw Fubini's theorem for a rectangular region, but more generally, we saw that it found the volume of whatever space we have. So my little chart here, for a double integral and the volume of a 3D object, you would do the double integral with your function in it, and then dx dy or dy dx. So we've seen that so far. Let's continue. So what if we wanted to find the area using double integration? The only difference now is that in our expression, we don't want to put like a function. We just put 1, and that gives you the area. So for example, we have find the area of the region R, where R in the xy plane is enclosed by y equals x squared and y equals x plus 2. Yes?
Do we find the area by just doing like one integration and the function?
I don't think so. I don't think so.
Wait.
Maybe. Not too sure. Let me think. I don't think so because like
Bound would be weird. Like, there's only one bound and multiple variables.
yeah. I mean,
If we do that in single variable calculus,
yeah.
finding the intersections and things like that.
Yeah, I guess if you're finding like in single variable calculus, like the integral from 0 to 2, you would do the function from 0 to 2. So I guess, yeah, it does.
But we cannot do it for multivariable. There's only one.
Multivariable, we're mostly going to be dealing with oh, okay. You mean like, so in this question, you wouldn't be able to do it with a single variable, like a single integral. Because then, unless it was like a triangular region, then you could do it with a single integral. But right now we need 2 equations in order to find this like weird shape. So that's why we have to do a double integral for this question. But if it was like a easier shape, then yes, you could do it this way. Okay, so for this one, if we're doing a double integral, so I wrote here in red that we don't want to do dx dy. The reason is because if we do dx dy, so first we draw a line in increasing x direction. So increasing x direction would be this orange one, right? Or it could be this second orange one. But depending on which line you drew, so like this top orange line, it would enter at this line, the x plus 2 line. But this orange line enters at y equals x squared. So you're entering at 2 different lines, so it doesn't really make sense to do the dx direction first. If you wanted to do the dx direction first, you'd have to split up your region into 2 separate parts so that you could do dx dy. So instead, we're going to do dy dx first. So dy dx, we draw a line in increasing y direction. So that's vertically up. It enters at this point, y equals x squared, and exits at y equals x plus 2. Out of all the possible orange lines we can draw, the least y value we get is this purple point, and the greatest y value we can get is that purple point. And how do we get those 2 points? Well, that's where your 2 equations intersect, right? That's the intersecting points. So if we set the 2 equations equal to each other so that we can find the intersection, we get x squared minus x minus 2 equals 0, x minus 2, x plus 1 equals 0, or x equals 2 and negative 1. So your x bounds go from negative 1 to 2. And you can continue the integration and get 9/2. Any questions on that? And so now you see that if we have a double integral and we want to find the area, do the double integral of 1.
Why one? Why the one?
Like this example. Because this double integral is already taking care of like the area of the region. And remember, this having a function in it basically means that, so we have this flat area, but we made it 3D. So that's why we took this function. Okay. Any questions up to this point? Yes.
Can you repeat how you decided to do dx against dy?
Yes. So if you were going to do dx dy, let me put it here. Oh, wait, I didn't draw it. If you wanted to do dx dy, you draw a line in the increasing x direction. So you draw like this first yellow line. The yellow line enters at x plus 2. So you get that x enters at x plus 2. Right, y minus 2. Because this line is y equals x plus 2, or we write it as x equals y minus 2. So it enters there, and then it exits at this line. That line is y equals x squared, or because we want to write it as x equals something, this is x equals square root 1. So that works for that line. But then what if you actually drew this horizontal line instead? Because remember, we're considering all lines in increasing x direction. But then this line would enter here, which is this parabola or square root y. And then it also exits at square root y. So we're getting two conflicting things here. So we can't have this like be conflicting. We should only get that our like line enters at one equation, exits at one equation. So we don't want to do dx dy. So we know that we should try dy dx instead. Yes.
So we don't want slices that go through or that go between functions. We want it to stay between the same two functions or not.
Yes, exactly. So if you wanted to do dx dy instead, what you could do, you would need to break this up into two regions. So like first take the integral of this triangle. And for this triangle part, then yes, you would use this bound for what x. But then you would have to add it to the integral of this white part. And the bounds for that would be using that. Yes.
The bounds of the second part, isn't it negative?
Yes. Okay. It's just like in single variable calculus where you sometimes have to like split up regions. Yeah. Okay. Any other questions on that? Okay. Then we have the average value of f over r. So the average value in general is always going to be either a double integral or triple integral of your function divided by that same like double or triple integral, but with 1. And specifically for the average value of f over some 2D region, you notice that this integral of 1 dx dy, we found that that's the area of our 2D region. So it's just the area of R. So sometimes if your region they give you like is a square, then you could do this double integral of 1, take the integral, etc. Or you could recognize that geometrically it's a square and just do the length times the width. So that will save you some time instead of actually computing out the integral. Okay. Okay, any questions on double integrals before I move on to triple integrals? Okay. Okay, so now we have the Fubini's theorem for triple integrals. And so, yes. So now we have triple integrals and we have a function dz dy dx. Okay, so triple integrals are a bit more trickier. Let's do this with an example. Okay, we have this tetrahedron and it says find the volume of the tetrahedron for the vertices are this. Okay. So first thing we should do is just draw out what even is this shape because we don't know what to do without knowing what it looks like. So let's draw this shape. So we have A is 0, 0. B is 1, 1, 0. So that's like around here. C is 0, 1, 0. It's around here. And then D is up here, 0, 1, 1. So it looks like a tetrahedron, four-sided shape. Okay, the first step we want to do is, and I tell you, let's use the order like dz, dy, dx. So the first step we want to do is find the dz bounds. So let me, okay, let me just continue. Let me see. So now we want to, so in the double integral case, we've been slicing lines in the increasing x direction or increasing y direction. Now we want to start with a line in terms of increasing z direction. So in the terms of increasing z direction, we're going up this way. And so does anyone want to tell me what plane does z enter? Yes?
0 and 1.
Yes. So z enters at z equals 0 because this triangle here, flat, is on the xy axis, xy plane. So x can be anything, y could be anything, but z is always 0. But then where does it exit? It exits at this plane, this yellow plane. So you want to imagine that, so it's kind of like crooked, but this BCD triangle, this is flat. This is a flat triangle. So any line that you draw upwards, it's always going to go through this top like triangle, ABD. And what is this upwards triangle? Well, we need to find the equation of this highlighted plane. How do you find an equation of a plane? You need a normal vector, and then you use your formula. So how do you find a normal vector? Let's take two vectors on our plane. Let's choose like BA. So if I choose BA, right, BA is going to be 1, 1, 0. Then DA is going to be 0, 1, 1. So now we have two vectors, AB and AD, or DA. If we take the cross product, we know that the cross product is always going to be orthogonal to this and orthogonal to this. So the cross product would give us our normal vector. The cross product is 1, negative 1. Yeah. And then we use the equation of a plane. What's the equation of a plane? You do the normal vector. Starting with, you can write x, y, z minus a point on our plane. Well, the easiest point on our plane we can pick is point A, which is the origin. So what is our normal vector? 1, negative 1, 0. Or I could just simplify this all. It's going to give me 1, x minus 0, minus 1, y minus 0, plus 1, minus 0, or x minus y plus z. And we're finding the bound for z, right? So we should have z equals something. Let's rewrite it. So z equals, subtract the x and add the y. So our exiting bound is going to be negative x plus y. Yes?
We're using that.
Oh.
from 2013.
Oh, sorry, I wrote this one. This is the one. Yep. Where did I put the chart? Oh. Okay. Any questions on how I got that plane? Okay, now that we have our z direction, the next step is we collapse the whole entire 3D shape. So if we collapse it, meaning think about you're looking at this from like a bird's eye view and you just see its shadow. If you look at it from the top, the shadow that you see is just going to be this triangle here, this green highlighted triangle. Or in other words, if I redraw that green triangle, so okay, let me keep this up here. If I redraw that triangle, I'm going to get, you can think about your points. So A without the Z point, just it gives you left with 0, 0. So this is our new A. B without the Z point is just 1, 1. So 1, 1. And C without that Z point is 0, 1. So 0, 1. So in the XY axis plane, this is what our shadow looks like now, after we've collapsed the Z axis. So now this becomes a 2D problem, which we just did in the beginning of class. We could do dx, dy, or dy, dx. So let's do dy, dx. For dy, dx, we draw a line in increasing y direction. Y enters here. What is this line? Well, our point is 1, 1 up here. So this line is y equals x. So y enters at x and it exits at y equals 1. Now, out of all the possible lines we could draw, the smallest x value we get is 0. The largest x value we get is 1. And so the triple integral, or the volume of this tetrahedron, is going to be, so we start with z from 0 to y minus x, y from x to 1, and x from 0 to 1. And if they give you a function, then this is your final answer. So if they ask you to find the volume of the integral of some function over this 3D region, this is going to be your integral. Any questions on this example? Yes.
A shape like that, like, how complex shapes do they?
I think this shape is pretty
Like,
reasonable.
yeah,
Yeah.
but like,
So they wouldn't be, so this shape is reasonable because this BCD plane is flat. If it was like not flat and it was like a pyramid or something, that would be because then you'd have to split it into 2 integrals maybe. So I think like that might be too time consuming. But I think this question is reasonable. Yeah.
The cross product between the vector BA and AD
Mhm.
is orthogonal to both of them,
Yes.
and therefore it's the normal vector, right?
Yes. Yeah. Okay. And for this question, I did dz dy dx, but you should note that if we wanted to change the order and do dy dz dx, it's also possible. And so I'll leave this as an exercise and see if you guys get these bounds. Yes.
so the question says finding the volume and
Okay, so in the wording of my question, it would be 1. Wait. Yes, 1.
and in what context would you put in the actual function, not this one?
If they said, let's see if I have an example. I don't have an example. Do I have an example here? They would say like, find the triple integral of your sum function over a 3D region. So they would give you the function and say, find the integral of this over a 3D region. Then you know that you should put in the function. Yes.
But I got confused. Why did you put a one instead of a function?
Because, okay, so let me continue filling in our chart. So we had the even more complicated convenience theorem. Like, triple integral of 1 dv gives us the volume of our object. So we saw that the double integral of 1 gave us just the area. The triple integral of 1 will give us the volume of some object.
So there's no area for the triple.
Yeah. So this is our nice chart. See how it goes like this way, and it goes that way. So that's like, this would be like the volume of some for the object. Entire dimension. Yes?
Could you project into like the x, y, and then also the z, y plane?
Yes, you can project to the dy plane. You'd be left with the triangle ABC.
You did that twice instead of like trying to find the plane.
What do you like?
Like project into the zy plane to find the dy value. Set all axes there. What did you get?
Yeah, I see. Yeah, it would work. It would work for this example. I'm not sure if it will. But I think it, actually thinking about it, it does generally work like that. Yeah. Okay, so let me do a reordering question. So you're given this left side, the triple integral of this f dz dx dy, and you're asked to reorder it to dx dy dz. So let me give you guys a minute to think about this and try drawing what region this gives you. Okay. Okay, does anyone have an idea for what this shape looks like? Yes? Yeah, yes, exactly. So it looks like a skateboard rim. So how do we determine that? Well, first, let's look at what this bound tells you. So in the xz plane now, this tells you that z goes from 0 to x squared. So wait, sorry. Yeah, z goes from 0 to x squared. So x squared z equals x squared is this line, goes from 0 to x squared. Then this bound tells you x goes from 0 to 2. So think about all possible lines in increasing z direction. X can be at least 0 and at most 2. So this is our region right now in the xz plane. So you can imagine that if you collapse the y-axis, this shadow is what it would give you. Then in 3D, you want to project this. So, oh, I should have, let me erase this. So right now we have in the XZ plane, this triangle shaped thing. Our bounds tell us that Y goes from 0 to 1. So we take this triangle thing and Y can be from 0 to 1. So we kind of like move it, this triangle thing towards us. And we fill in what that shape is. And so this kind looks like a skateboard ramp. So there's like a curve here. Any questions on how I got that shape? Okay, so yes. Yes.
Oh, because they're all.
Yep. Okay, so we're asked to reorder it from dx, dy, dz. So we start in the increasing x. So let's draw a line in the increasing x direction. So that's this orange line. So x enters at this curve, this green curvy part. What is that curvy part? Well, we were given that z equals x squared. So this kind of goes back to I think Javier, right? You said if you kind of like project it to the xz plane, what is that line? That line is z equals x squared. So in general, this plane, this green plane, also turns out to be z equals x squared. So z equals x squared. But we want to write things in terms of x equals something. So if I square root both sides, and we only want the positive version since we're in the positive quadrant, so x enters at square root z. Where does x exit? Well, that's the plane x equals 2. Then we project to the yz plane. So get rid of x and everything like moves that way. Think about the shadow. So if everything projects down, you're kind of left with this square thing in the yz plane. At this point, it's now like a 2D region, so we could use our 2D methods, and we want to do dy. So write a line in the increasing y direction. Y starts at 0, exits at 1. Out of all those lines, what is the smallest z value? That's 0. Largest z value is 4. So this would be the reordering of your integral. Any questions on that?
It is as hard as it can get, right?
I think so. I mean, with these bounds, it's always like tricky to like once you see it, you're like, oh wow, that makes sense. But if it's like something new, it might look more trickier. But yeah. Okay, speaking of that, I have another example. So you're given these, so you're asked to find the volume of some solid. That solid is made of these 3 cutouts. So these cutouts are saying like, if you look at the shadow, project, so like get rid of the z-axis, collapse the z-axis in the shadow of the xy plane, you get this. In the xz plane, you get this. In the yz plane, you get this. So let me also give you like 30 seconds to think about what shape does this give you? What 3D shape is this? Okay, anyone have any ideas? Yes.
Is it a kind of like here like this?
Yes, exactly. So, okay, let's work through it. So the cutouts tell you, so in the XY cutout, we see, oh, sorry, Y goes from 1 to 3. So imagine this is our XY plane, right? Y goes from 1 to 3. So 1 to 3, and it kind of goes out to X equals 2. So it kind of looks like this. Oh. So in the XY plane, we get this cutout. If you like collapse the Z-axis, look at the shadow, it looks like that. In the XZ plane, X goes from 0 to 2, and Z goes to 4. So we kind of have this like rectangle here, and we have another like rectangle here. Then in the YZ plane, we have a kind of like parabola thing. So Y goes from 1 to 3. So this is exactly the YZ plane. Looks like that. So let's draw what that looks like. And then we want to kind of fix our shape. So if we get rid of like these lines, it kind of looks like a dog house or a tunnel, like that. So see how I looked at all the cutouts, and I saw what shape does it give me. So like if you're just given this shape and you were asked to like find the bounds, think about how would you project it. Like when you collapse one of the axes and you see that you get these 3 shapes. Any questions on how I got this drawing? Yes?
Like it isn't touching the axis, like in the drawing it doesn't look like it.
Oh, so in the drawing, it doesn't look like it's touching because our Y starts at 1. So it's kind of like out here. But remember that the cutout is telling you if we got rid of this Y axis, so we projected everything this way, then it looks like it's touching the Z axis. If you just project it, it would project to this kind of like background rectangle. But it doesn't matter that it's like out here right now.
Okay.
Any other questions on this picture? Okay, so if you were to find the volume, now we just need the bounds, right? So what are the bounds? Well, they conveniently tell us that the maximum Z could be is this equation. So Z happens to go from 0 to that equation. If we collapse the Z axis, that means we're left with XY plane. And that cutout was this cutout here. So Y, if we draw a line in increasing Y enters at 1, exits at 3. Out of all those lines, X, smallest value is 0, largest value is 2. And so this would be your triple integral. And because you're just finding the volume of this, what was our formula? Volume of 3 objects, triple integral, we found bounds, and you just put in 1. Okay, and you can evaluate that and you'll get 32 over 3. Yes.
So I've seen that like basically when you like perform the first step in getting you essentially get volume of a 3D object with a double integral. And this thing where it's like a function of x and y and stuff. So how would we? Is there any way to like go immediately to that from the kind of like 3 variable thing that they're giving us, or do we always like create a triple integral with the one?
Like you're saying, like, is there any way to get this like get to this step immediately? Kind of.
Yeah, I guess not, right?
Yeah, I don't think so.
And that's not even, is that even considered f of x and y because it's only in y variables?
Yeah, it's okay if it just has Y values. It just has at most X and Y. Like you can't have a Z in there.
Okay, cool.
Okay. Any other questions on this example? Okay. Oh yeah.
Yeah, sorry. So then in the situation which we would use the double integral
line with your job, which it would kind of set up the problem where there would only be X and Y, and they would expect us to do it in that way.
Yes. So if it was a double integral, this like double integral, like the region they give you would be have to be a 2D region. Whereas for this one, the region they give you, so I write D for like this, or I don't know how it's D, but it's like a 3D region. Yes.
So like, say if the first function was in terms of like y and like x, like you wouldn't be able to project it in like both planes, right? Like you have to choose one.
What do you?
Like once you project it, you have like one that's in terms of like it's in between like a function and like a constant. Then the other ones are in terms of like in between two constants.
Mhm.
But if it was like a weird shape where like when you projected it, it wasn't in terms of like constant.
Then you would have to find what is that equation. So that would be like
Like that would just be setting the first one.
yeah, exactly. Me. Yeah. Okay, and for this one, the order I chose was dz dy dx, but note that you could have did a different order. If you tried doing dy first, then like dz or dx, or dx dz. So if you want to start with dy, that's fine, because y would enter at this. Let me see. Yeah, it would enter at this plane and exit at this other plane.
Would it be that way around?
Oh, yes, yes, thank you. So you would enter at this plane and then exit at this outer plane. And you project it down, you're left with the XZ plane, or plane, plane cutout. So XZ plane would be this cutout. But if you try to do DX first, then we run into a problem like the similar from a few minutes ago, where if you draw a line increasing up, one side would exit at this outer plane, but another line might exit at this like back plane in the back. So then you can't do DX first because you're exiting at two different planes and you don't want that. Does that make sense?
With DX, so that's,
If you wanted to do DX first.
yeah, X is going from there.
X. Oh, sorry. Oh, wait. DX. Oh, wait, yeah. Did I? Okay, maybe DX.
But it always be a constant thing. So that would,
Let me think. DX.
you can't end
Wait. Because you would enter at this like backwards plane and exit at this frontwards plane.
I guess wouldn't the issue be if you ended with Z, then you'd end with something that's defined in the terms of another variable. You can't end a definite integral in terms of another variable with the last bound calculation.
Yeah, that's the problem. Yes. Because if you did DX first, then you'd be left with this thing in the X in the ZY plane. So you'd be left with this thing. But then if you wanted to do like in the DY direction first, this entering point is the same as the exiting equation. And so you can't do that integral through the same. You want two separate ones. So that's why doing DX first doesn't work. Yes. Thank you. Any questions on that?
We could do dy first as long as we change the equation of 16y minus 4y squared in terms of y first, in terms of c first.
So either, yes, either Z or Y can be
Let's see. And then, so we've learned, yes, so that's the little chart there. And then finally, if you have like average value of f over a region, now it's the same thing as the average value over like the 2D region, except we have triple integral. So you do the triple integral of your function over the triple integral of 1. And so as an example, if you're trying to find the average value of f over d in a space, where f is this equation and d is this 3D region now. When you do the average, so you have triple integral of f, that's fine, you have to compute that. But for the volume, note that if you try to do the triple integral with 1, you would get 8. But you could also recognize that this gives you a rectangular box. The reason we know it's like either a cube or a 4D cube or ND whatever cube is because the bounds are numbers. When the bounds are numbers, it's usually like a square or box, etc. So the volume of this, x between 0 2, that gives you like the length of one side. The length of x, the x side is 2. The length of your like width is 2. Your height is 2. Volume is 2 times 2 times 2, which is 8. So sometimes in order to save time, maybe finding the triple integral of 1, see if you can recognize if your solid is like a solid we're familiar with. Okay. Any questions on that? Yeah. Yes. So I have a comment. I think if you're trying to do like, for example, like a 4D solid and like you had to put 4 integrals, then the volume would just be like whatever x, the length of x, length of y, length of z, length of w. And it works for n-dimensional cubes too. Do the same thing. Okay. Any other questions? All right. So today is Wednesday, but does anyone know what Monday was? Yay. Okay. And does anyone? Oh wait, let me stop this recording real quick.